My name is Yamin Friedman, and I'm a hardware architect at NVIDIA Networking, specializing in storage solutions. And I'm here today to talk to you a little bit about some performance challenges that we came across while optimizing our storage solutions, and discuss the challenges themselves, the performance limitations, and how we managed to overcome them by optimizing the software stack. And I would also like to introduce Rob Davis, who is a VP of Storage Technologies at NVIDIA Networking, and he's going to start by giving you a short introduction before I start my deep dive into the subject. So Rob, take it away.
Thanks very much, Yemen. Hello, everybody. I'm going to start off with some background on NVMe-oF Fabrics, RDMA, and the solutions that can take advantage of the performance improvements Yemen is going to talk about in detail later. The first question you might ask is, why do we care about improving the performance of our NVMe-oF Fabrics solutions? Or for that matter, why do we care about Fabrics in general? And the reason is because NVMe SSDs are really fast, and they're getting faster every generation. 4 of today's PCIe Gen 3 NVMe SSDs can almost fill a 100 gigabit Ethernet interface. And with the Gen 4 SSDs already sampling, it will only take 2. A 10 gigabit Ethernet interface, the sweet spot for 24 hard drives in a JBOD, can't even come close to supporting the performance of one first-generation NVMe SSD. NVMe SSDs have moved the storage networking bottleneck from the disk to the network. Of course, with 100 and 200 gigabit Ethernet and InfiniBand controllers, adapters, switches, and cables available today, and 400 gigabit on the way next year, you might think the network bottleneck problem is solved. But faster wires is only half of the problem. We also need faster protocols. That is because as the storage media gets faster in comparison to the network hardware performance, we can't forget the efficiency of the protocols running on the network. This graph shows the relationship between the performance of the storage media and both the network hardware and the storage network protocols like NVMe-oF Fabrics. And we can't forget the network transport protocol underneath NVMe-oF Fabrics. The most efficient and highest performance transport protocol for NVMe-oF Fabrics are RDMA based. For Ethernet, this is ROCE, RDMA over Converged Ethernet. And you can also use InfiniBand for NVMe-oF Fabrics, where RDMA support is the default. NVMe-oF Fabrics takes the new NVMe high-performance SSD interface and enables it to be connected remotely across a network. It works by encapsulating the local NVMe commands inside the NVMe-oF Fabrics protocol, sending it across the network, and then de-encapsulating them and sending them to the remote NVMe SSD. This gives us all kinds of advantages over local NVMe storage. It is basically infinitely scalable, extremely reliable, and very efficient from a power, cooling, and rack space perspective. And it's much easier to manage than local storage. NVMe-oF Fabrics, the NVMe-oF Fabrics standard was developed by players from across the storage industry at NVMe.org, who also wrote the NVMe standard. And version 1 was released in 2016. It bypasses legacy storage stacks. And when RDMA transport is used, legacy network stacks are bypassed as well. All the first generation NVMe-oF Fabrics products were based on RDMA for the highest performance. And the performance is impressive and close to local NVMe performance. This data is from an early article at the URL below the graph. It is not uncommon today to see the performance differences as low as 5 microseconds. RDMA is the remote version of DMA, direct memory access. DMA is a hardware-driven transfer of data from memory to memory within a computer system. No software is involved in the data path. RDMA is a hardware-driven memory-to-memory transfer across a network performed by the InfiniBand and Ethernet adapter hardware. And again, no software is involved in the data path. Instead of the network transport layer being in software, with RDMA, it is in hardware on the network adapter. So because software is not involved, you get lower latency, higher bandwidth, and lower CPU utilization. You can easily see the performance differences with Microsoft SMB that supports both RDMA and TCP modes. When RDMA is turned on, the performance doubles, the latency is cut in half, and the CPU utilization drops by 1/3. You can watch a live demo of this from a Microsoft event on YouTube at this URL below the graph. So what applications need this level of network storage performance? Here are 3 common use cases. The first, on the bottom left, is what I call classic SAN, only at NVMe over fabric performance levels instead of fiber channel or SCSI. Many applications that use SAN-based storage need very high performance, for example, large databases. There are also new applications using SANs today, artificial intelligence and machine learning, for example. In fact, the new GPU direct storage, part of NVIDIA's Magnum IO initiative, only works with RDMA-based networks, or network protocols like NVMe over fabrics. Another common use case for NVMe over fabrics is a back-end cluster for capacity, scale-out, and high availability. That's the center top on this slide. Inside most high-end storage systems is a small network of NVMe over fabric nodes that provides these functions. And lastly, at the bottom right, is a new application that NVMe over fabrics actually enables with its performance, and that's called compute storage disaggregation. It is sometimes also called composable infrastructure or rack scale. Here, instead of having compute nodes in the data center configured with the amount of storage and compute needed for each application type in the data center, you disaggregate the compute from the storage with NVMe over fabrics. Now, depending on the application's storage and compute requirements, you use the network to connect them using NVMe over fabrics protocol. And with this kind of performance, most applications can't tell the difference between local and remote storage. So why, with this kind of performance already, 5 microseconds off of local drive, do we need to make it even faster? And the reason is technology never stands still, especially at the top of the storage performance pyramid. PCI Gen 4 SSDs are coming out this year. They will be twice as fast as today's Gen 3 devices. And in another couple of years, we will have Gen 5 that will be twice as fast again. Then there is persistent memory, which is an order of magnitude faster than NAND-based SSDs to start with. Besides performance, the major feature of persistent memory is, of course, its persistence. But for one of the biggest markets, the enterprise, persistent memory's persistence capability is simply unusable unless it has high availability, which means a very high performance storage network. Persistent memory also needs to be able to expand its capacity by more than what a single server can hold. Again, with a fast enough network, this can be done by connecting many servers together to form a much larger pool of persistent memory. And this is just a couple of many persistent memory applications that require a high-speed network. And with that, I will turn this back over to Yemen to tell you how we can make NVMe over fabrics even faster to make existing use cases better and address some of the new ones I have shown you. Yemen?
Thanks, Rob. So what I want to start with the discussion of today is system interrupt overload. So what are system interrupts and what is system interrupt overload? So in order to handle networking traffic, the kernel uses interrupts to inform the software to allow the hardware to inform the software that packets have arrived on the network. In NVMe-oF Fabric storage flows, there may be multiple interrupts per I/O because each I/O may include several networking transactions. What we found is that when the system is overloaded with a large number of interrupts, it interferes with the ability for the network adapter to perform RDMA and transfer the data from the adapter to the CPU. So I'm going to show a few test results throughout this presentation. So the setup that I used was 2 Intel Xeon CPUs using 28 cores on each side, Linux version of 5.7 with the added feature of shared CQs, and the network adapter of Mellanox ConnectX 5 EX, now NVIDIA ConnectX 5. So in this graph, which is a graph demonstrating the issue that we came across, we see that the orange line is the K IOPS that we managed to receive given a number of cores that we are using. The green line at the top shows the wire speed of the 100 gigabit Ethernet wire that we were using. And we can see that as we scale up the number of cores, the number of interrupts per second goes up very quickly. And once we reach a certain amount of scale, our performance not only does not manage to reach wire speed, but it goes down at a certain point, at which point it reaches a steady state as we increase the scale. So this obviously is not a good condition, as we have hardware that allows us to reach 100 gigabit Ethernet, and we would like to be able to enjoy all of that bandwidth for our storage. So we came up with 2 solutions to this problem, and I will talk about each of them in turn. So the first one is called dynamic interrupt moderation, or DIM for short. So what is interrupt moderation? Interrupt moderation is a method to allow us to perform more work for each individual interrupt, which allows the CPU to be able to more efficiently handle the work that is required of it without having to always be interrupted and switch contexts, and the overhead for interrupt handling is just too large, and we would like to reduce that. So RDMA completion queues are able to be configured so that they arm a system interrupt only once either enough work has been gathered or a specific timeout has been reached, which means that if the first packet that arrives, and if you have set your moderation to wait for 4 packets, so you will wait to activate the interrupt until you have 4 packets, at which point the CPU can poll the completion queue and handle all 4 at the same time. The problem with this is that there's no single configuration that will be optimal for every system, and for even the same system over time is going to have different traffic patterns that will have different requirements of bandwidth and latency. And in general, interrupt moderation might harm latency, as you are delaying when you will react to the work that has arrived until you have more work so that you can handle it more efficiently. So dynamic interrupt moderation comes to avoid the issue of static configurations and allow us to reach the optimum amount of interrupt moderation for the system at the given time. So interrupt DIM adapts, it collects statistics of the work as the work is occurring, and it adapts the current state of the interrupt moderation to maximize performance without too much of a cost in latency. So over time, it alters the interrupt moderation parameters to maximize performance. So the DIM algorithm collects a couple of different statistics, and it has 3 stages of algorithm. So the statistics that we collect are the number of completions polled within a specific amount of time, and the number of interrupts that were required to poll all of those completions. So the first stage is to optimize for the number of completions. The number of completions is a good indication of how well we are how efficiently we are performing work, because as we said earlier, each IO has a specific number of completions that are required for the IO to be completed. So the more completions you complete, the more IOs you are finishing, and so we are getting better performance. The second stage is to optimize for the ratio of completions to interrupts. So for a given amount of completions per second, we would like to reduce the load on the system as a whole by reducing the amount of interrupts that are required to poll all of those completions. So the ratio gives us a good indication of the effectiveness of the interrupt moderation, because if the ratio is high, then we are effectively performing the moderation, polling a lot of completions per each interrupt. The third stage is very important for storage applications that can be very sensitive to the latency of the operations. So here we need a method that if the moderation is low, is ineffective, and the ratio is low, then we would like to quickly reduce the moderation so that we will not suffer with long latencies that aren't necessary. So now we will look at some performance results of using the DIM mechanism. So as we see, the orange line is what we saw previously, which is the K-IOPS without DIM, and the blue line is with the DIM mechanism. So as we can see, as we scale up the number of cores, not only do we reach the wire speed of 100 gigabits per second, but we maintain that rate as we scale up the number of cores. We also see by the yellow bars that the number of interrupts per second, not only is it significantly lower than it was before, but now we have a linear scale up with the number of cores, which is what we would expect to see with an efficiently working system. On the graph on the right, we see the latency for 4 kilobyte read IOPS. And we can see also here that with DIM, we see better latency at all scales, which indicates that our method of preserving latency was effective. So we see similar results also for 4 kilobyte write IOPS. So we also here see that the bandwidth quickly reaches the line rate and maintains that rate steadily at scale. So that is the DIM feature. And so the second feature I would like to discuss is shared completion queues. So as we saw previously, DIM is very effective in reducing the amount of interrupts per CQ because it was built on a mechanism where each CQ individually adapts to and performs interrupt moderation. But what do we do when we have many applications? Now, An application, for instance, would be NVMe-oF Fabric's storage device, and a specific connection to a single disk is going to open their own CQs, one per core, so that we have high availability. So if you are connecting from the same server to many disks, or even just 4, then we're going to open 4 CQs per core and spread the traffic over all of those CQs. So each CQ will only be able to perform interrupt moderation on effectively 1/4 of the traffic. So the Linux kernel driver provides CQ interrupt handling as a service to applications. The application itself does not poll the CQ to find out when work has been completed. Instead, the kernel driver uses interrupts to identify when work has arrived and then notify the application that the work is completed and that it can continue its work. So in this model, the fact that each application is opening their own CQs is inefficient because they are all receiving the same service from the kernel, and it is not providing them with any added functionality to know that they are the only ones using that completion queue. So with shared CQs, we provide an API that provides full functionality for the applications, but allows them to share a single CQ per core, reducing the system overhead and allowing the kernel to more efficiently handle the work. So here's another test where we are connecting this time, instead of to 1 disk, 4 disks from the initiator, and running traffic to all of them at the same time. So this is 4 kilobyte read IOs. And in this case, the orange line is indicating for a system that is using DIMM, but not using shared CQs. And the blue line is with shared CQs and DIMM. And as we can see, without shared CQs at around 13 or 14 cores, we start seeing a very rapid increase in the number of system interrupts as a whole, interrupts per second. And at that point, the performance starts going down and degrades steadily as we increase the scale. Whereas with shared CQs, we managed to maintain the low level of interrupts per second, the linear scale up with number of cores, and we managed to maintain high performance with only slight degradation as we increase the scale. And we can see that the latency is also improved at that higher end of scale. Again, similar performance for 4 kilobyte read IOPS, write IOPS, sorry. And I would like to mention at this time that I'm not going to go through various graphs of all the different sizes of IOs, but these performance improvements are continued for IOs that are smaller than 4K, down to 512 bytes. We still see the same significant improvement. At higher sizes, for instance, 64 kilobyte IOs, we don't see the same level of improvement using these features because at those sizes, we don't have enough interrupts in the system to reach the state of system interrupt overload. So in conclusion of this work, so a couple of comments. We discovered a hardware limitation on commodity servers for handling interrupts during RDMA. As we saw, as we scale up, the system as a whole reaches a specific amount of interrupts per second. And at that point, we cannot handle any more interrupts. And that limits the rate of RDMA that we can perform. We provided two features that have been submitted and accepted to upstream Linux to overcome this limitation. And this allows everyone to enjoy a more streamlined software stack for their NVMe-over Fabrics RDMA storage solutions. And with these features, this helps enable the use of the latest generation of NVMe SSDs, as well as persistent memory, to allow and fully utilize the performance that they provide. A couple of key takeaways that I think are relevant for based on this work is the fact that while optimizing our storage solutions, we may come across bottlenecks throughout the hardware and software stack. And these bottlenecks may require solutions that either need to be very flexible, as in the case of DIMM, where we do not have a single configuration that is optimal, and we need to have a solution that can adapt to changing circumstances, and perhaps cross abstraction layers, as we saw with the shared CQs, where what was previously thought to be the correct abstraction to the application of a completion queue is no longer optimal, and that we would like to abstract the hardware resource of a completion queue from the application, have the kernel handle the resource itself, and that way we can be more streamlined and more efficient in our handling. So that concludes our talk for today. If anybody has any questions or comments or would like to discuss any other subjects with Rob or myself, they can contact us at our emails. And thank you very much for your attention. And I hope you have a enjoyable conference. Thank you.